Hello, and welcome to our latest webinar, Exploring Stability and Flowability in Food and Beverage, brought to you by Lab Compare and sponsored by Bettersize. My name is Michelle Taylor, Editor-in-Chief of Lab Compare, and I will be your moderator throughout. We have a great lineup scheduled to present to you today, but before we begin, I'd like to cover just a few logistics. At the end of the presentations, we will hold a question and answer session. To ask a question, click on the Ask a Question tab in the upper right corner of your screen. Please also take note that the right side of the screen features an overview of today's webinar, as well as more information about our speakers. If you have a technical question during today's event, click on the Test Your Connection button at the bottom of your screen. From there, you can access additional webinar support. We also invite you to use the social media widgets beneath the webinar to share with your friends and colleagues. Today, you will hear from Beverly Barnum, a senior application scientist at Bettersize. She received her Bachelor of Science degree in chemistry from California State University and earned a PhD in organic chemistry from the University of Pennsylvania. Recognized for innovative problem solving, Dr. Barnum is a highly accomplished scientist committed to advancing technological solutions. You will also hear from Viola Shen, an application scientist at Bettersize. At Bettersize, Viola focuses on optimizing particle analysis methods, driving innovations in the advanced materials industry. She specializes in powder characterization and particle size analysis using advanced light scattering techniques. Viola holds a master's degree in chemical engineering from the University of Southern California. Thank you for joining us for today's webinar. Now, I'm going to hand us over to Beverly to get us started.
Thanks for that kind introduction and this opportunity to talk to everyone today. The food and beverage industry is a vital part of human life, providing people with necessary nutrients and energy to survive. It's a major contributor to the global economy and environmental sustainability through resource consumption, pollution, and waste generation, including greenhouse gas emissions, water usage, and usage of plastics. The food industry in 2025 faces unprecedented challenges, from supply chain disruptions to rising production costs and evolving consumer demands. Despite projected growth in the trillions, businesses are grappling with economic uncertainty, regulatory pressures, and sustainability concerns. At the same time, food waste continues to be a significant issue, with nearly 30% of global food production lost or wasted annually, highlighting inefficiencies across the supply chain. Challenges include these supply chain disruptions, climate change and sustainability, labor shortages and workforce management, the need for new technological advancements and integration related to updating operations, but also the rise of alternative proteins and lab-grown food products, which require engagement with regulators, leading to product-related challenges like food safety, quality control, along with the changing consumer preferences, and finally, regulatory compliance and food fraud. The objective of this webinar is understanding the impact of stability and flowability on product quality, manufacturing efficiencies, and consumer experience. Why stability and flowability are critical in food, beverage, and manufacturing, and what are the key challenges faced by manufacturers and how innovation addresses them. In the food and beverage industry, stability refers to the ability of a particle system, such as a suspension, emulsion, or even a powder, to maintain its size distribution and resist changes over time due to degradation modes such as aggregation, sedimentation, or dissolution. Stability is crucial for ensuring consistent performance in food products to avoid undesired changes in texture, appearance, and shelf life. Flowability refers to the ability of a powder or granular material to move freely and consistently under specific conditions, such as gravity or mechanical force. It is influenced by factors such as particle size, shape, surface texture, moisture content, and bulk density. Materials with good flowability exhibit smooth movement, while poor flowability can lead to clumping, segregation, or inconsistent processing. Stability is typically measured using techniques that track changes in particle size distribution over time. And some of the common methods include dynamic light scattering. This product monitors fluctuations in scattered light intensity caused by Brownian motion. This is used to assess the particle size distribution of particles in suspensions, revealing insights into their stability. Laser diffraction. By analyzing how particles scatter laser light Researchers can assess size distribution monitored over time and can detect aggregation or sedimentation changes over time that are affected by stability. Zeta potential measurements. This evaluates the surface charge of particles in suspension, which influence their ability to repel or attract each other, directly affecting stability. There's microscopy and image analysis, where direct visualization can help identify changes in particle morphology, and you can directly visualize aggregation. Finally, sedimentation and centrifugation tests can assess how particles settle over time, indicating stability in liquid dispersions. Stability plays a crucial role in the food industry, influencing everything from product shelf life to supply chain reliability. In food formulations, stable emulsions and suspensions, this ensures consistent texture, taste, and appearance, preventing undesirable changes like phase separation or sedimentation. Stability also affects food safety, as unstable products may degrade faster, leading to spoilage or contamination. In the broader industry, supply chain stability is essential for maintaining steady production and distribution. Sustainability efforts in the food industry also depend on stability, as companies work to reduce waste and improve resource efficiencies. We can break down stability into two categories: chemical and physical. Chemical stability refers to the ability of a food product to maintain its original composition without undergoing undesirable chemical changes. Factors affecting chemical stability include oxidation, where exposure to oxygen can cause spoilage, turn fats rancid, and result in loss of nutrients. pH changes can affect texture, flavor, and preservation based on changes to acid or basic. Naturally occurring enzymes can cause degradation, such as browning in fruits, but also vitamin C breaks down in juice, and there's loss of nutrients in stored products. In terms of light and temperature, UV light and heat can accelerate chemical reactions, which lead to the nutrient loss or spoilage. Fermentative microbes can produce gases like carbon dioxide, which lead to undesired change in package integrity and product consistency. Physical stability, on the other hand, involves maintaining the appearance, texture, and structure of food products. Influencing factors include moisture migration, where water movement between ingredients can cause texture changes, such as sogginess or drying. Phase separation. Emulsions such as salad dressings can separate if stabilizers will fail. Crystallization. Sugar and ice formation can impact texture and quality, causing sugar crystals and honey and mechanical damage, or breakage or crushing during handling can compromise product integrity. Solutions to some of these challenges include chemical stability, use of antioxidants, which prevent oxidation, antioxidants, and extend shelf life. Examples of this are vitamin C or tocopherols. pH regulators can maintain acidity and prevent degradation. Examples of this would be citric acids or phosphates. Encapsulation can be used to protect sensitive ingredients from environmental stresses, such as temperature. And chelating agents can bind metal ions to prevent unwanted reactions. An example of this would be the use of EDTA. Physical stability resolutions include emulsifiers, which can maintain uniformity in liquid formulations. Examples of this are lecithin, mono and diglycerides, and polysorbates. The use of thickeners and hydrocolloids can improve texture and prevent phase separation. The moisture control agents can regulate water activity to prevent crystallization or caking. Homogenization and mixing techniques can ensure consistent particle distributions. Proper storage conditions can also emphasize physical stability. New progress has been made with more advanced research to prevent separation. Emulsion stability has been advanced, where researchers are now developing biopolymer-based stabilizers and biodegradable emulsifiers to enhance sustainability while maintaining product consistency. and stabilizers, which improve viscosity and texture and prevent phase separation, includes factors like xanthan gum, carrageenan, and pectin. It's often seen in ice cream. Homogenization methods have been improved where mechanical breakdown of fat globules create a stable emulsion, which is used in dairy products and sauces. Modified atmospheric packaging, known as MAP, reduces oxygen exposure and slows oxidation and microbial growth. pH control can inhibit spoilage bacteria growth using ingredients such as citric acid. To affect thermal stability, advanced encapsulation techniques help protect heat-sensitive ingredients like vitamins and proteins during processing. The use of natural preservatives, including antioxidants like vitamin C and rosemary extract, can extend shelf life as customer demands changes away from chemical to natural preservation. Automated QC monitoring of viscosity, moisture levels, and ingredient dispersion can improve stability. And optimized bulk handling prevents segregation, which ensures uniform blending during processing. Moving on to flowability. Flowability plays a crucial role in the food and beverage industry, influencing everything from ingredient handling to final product quality. In powdered ingredients like flour, sugar, and protein blends, good flowability ensures efficient mixing, packaging, and transportation, reducing production delays and waste. In beverages, flowability affects the consistency and stability of emulsions and suspensions, impacting texture and mouthfeel. Poor flowability can lead to clogging in processing equipment, uneven ingredient distribution, and inconsistent product performance. Flowability is measured using various techniques to ensure efficient processing and consistent product quality. Some common methods include angle of repose, which measures the natural slope formed by a powder when poured onto a surface and indicates how freely it flows. Shear cell testing evaluates powder cohesion and flow behavior under different stress conditions, helping optimize handling processes. Bulk density measurements determine how tightly particles pack together, and this influences their flowability in storage and transport. Powder flow testaments are instruments that are designated to simulate real-world conditions, assessing flow properties under varying humidity and pressures. Rheological analysis is used for liquid-based products, measuring viscosity and flow characteristics to ensure smooth processing. Again, flowability refers to how easily powder moves and disperses in production environments through production equipment and packaging lines. The factors that affect flowability include particle size distribution and shape, which affect their movement. Moisture content and hygroscopic behavior, where moisture absorption leads to clumping or uneven distribution. Bulk density and ingredient composition impacts processing efficiency and surface characteristics. Flowability presents several challenges that can impact efficiency, product consistency, and equipment performance. And key issues include powder cohesion. Fine powders such as flour or protein blends tend to clump due to moisture absorption, and this leads to inconsistent flow and processing difficulties. Segregation. This arises from differences in particle size and density, which can cause ingredient separation, and this obviously affects uniformity in formulations. Poor flowability can lead to clogging in hoppers, conveyors, and mixing systems, which increases downtime and maintenance costs for equipment. Moisture sensitivity, where excess humidity can alter powder behavior, which causes stickiness or caking, and this affects handling and packaging. Flow measurement accuracies ensure precise control of liquid and powder flow rates is critical for maintaining product quality and minimizing waste. Improving flowability optimizes material properties, ingredient handling, equipment design, and environmental conditions. Some effective solutions include ingredient modifications, where adjusting particle size, shape, and moisture content can enhance flowability. Adjusting particle size distribution can enhance the flowability because finer particles tend to clump together, while larger ones may segregate. Granulation and particle modifications, where we use techniques such as spray drying or agglomeration, improve product shape and density, which leads to smoother flow. In surface treatment and additives, where applying anti-caking agents or flow agents like fumed silica can reduce interparticle friction, prevents powders from clumping. The use of flow aids and moisture control solutions prevent powder clumping, ensures smooth dispersion to optimize ingredient blending. Optimizing the formulation by selecting the right ingredient ratios and processing conditions will maintain uniform texture and appearance. Optimizing equipment design, where the use of specialized pumps and rotary joints can ensure a smooth fluid movement, reduces blockages, and improves efficiency. These enhanced powder handling technologies are used to prevent clogging through the manufacturing system. Custom designed hoppers, bins, and feeders can ensure the consistent flow by minimizing obstructions like arching and rat holing through the use of vibration or agitation techniques and through moisture control. Again, this leads to environmental controls where managing humidity and temperature prevents powders from absorbing excess moisture. And this reduces moisture-related flow issues such as stickiness or caking. Finally, using tools like shear testers and angle for pose measurements can help predict powder behavior and refine handling processes. In terms of advanced filtration system, high-efficiency strainers remove contaminants and improve consistency in liquid processing. Advanced blending and handling methods for uniform ingredient distribution. Equipment advancements such as fluidization systems are used for better powder distribution. And finally, with the advances in AI-driven monitoring detects potential flowability issues before they disrupt production. So balancing stability and flowability in food and beverage products requires careful formulation and processing techniques to ensure both consistency and ease of handling. Stability ensures that products maintain their intended texture, composition, and shelf life, while flowability affects how ingredients move through the production system. Some of the key strategies here include, again, optimize ingredient selection, use emulsifiers, stabilizers, and anti-caking agents to maintain product integrity and ensure a smooth flow. Particle size and shape control. Adjusting the particle characteristics can prevent clumping and improve uniformity in powders and liquids. As we mentioned many times, controlling humidity and temperature minimizes moisture-related flow issues and prevents degradation. Advanced processing techniques, again, like spray drying, encapsulation, homogenation, can enhance stability while maintaining efficient flow. With the advances in AI and smart sensors, these analytics can help detect potential stability or flowability issues before they impact production. On a large-scale production, maintaining consistency requires the combination of quality control measures, technology integration, and supply chain optimization. Some key insights here are the use of standard operating procedures, SOPs, which establish clear guidelines to ensure uniformity in production, reduce variations in taste, texture, and nutritional value. Automation and statistical process control, SPC, where real-time monitoring and automated alerts help detect and correct deviations before they impact product quality. Ingredient sourcing and quality assurance. Working closely with suppliers to conduct regular testing ensures raw materials will meet required standards. Testing of food and beverage ingredients to ensure that they meet these standards involves several analytical and quality control methods. Some of these approaches include chemical analysis, where techniques like HPLC and gas chromatography can verify ingredient purity and detect contaminants. Microbiological testing will ensure food safety by identifying pathogens and spoilage organisms. Physical property evaluation, where measurements of attributes like moisture content, density, and particle size will help maintain consistency. Sensory testing to assess taste, texture, and aroma will ensure customer satisfaction. And of course, regulatory compliance checks will verify the adherence to food safety standards such as FDA, USDA, ISO standards. In terms of supply chain management, efficient inventory control and logistics optimizations will help maintain consistency while minimizing waste and delays. Regular audits and consumer insights can define and drive refinements in product processes to meet evolving expectations. Best practices for ensuring stability while maintaining smooth ingredient flow is a strategy used for large scale production. Again, using ingredient optimization, adjust particle size, moisture content, and formulation to enhance stability and flowability. Processing techniques with homogenization, encapsulation, and emulsification to maintain our product integrity. Environmental controls, I cannot understate this. Again, managing humidity and temperature, storage conditions to prevent ingredient degradation. Again, the advancement of AI and smart machines will help detect potential flowability issues before they disrupt production. Some real world examples of food manufacturers successfully addressing stability and flowability include the following. Nestle brands implemented precise ingredient blending to ensure uniform texture and taste across global markets, utilizing automated blending systems to ensure accurate ingredient ratios. They utilized fast prototyping and testing to refine their formulations and partnered with academic institutions and industry specialists to enhance their ingredient uniformity. PepsiCo leveraged real-time viscosity monitoring to maintain their beverage consistency. They integrated automated QC systems into their production lines with advanced sensors to measure viscosity, temperature, and blend accuracy. This allowed them to maintain uniform texture and mouthfeel across batches, which reduced waste and optimized ingredient usage by early detection of inconsistencies and ensuring compliance with industry standards for product quality and safety. Finally, General Mills adopted an automated bulk handling system to optimize ingredient flow through their systems and reduce waste, transitioning from smaller 50-pound bags to 2,500-pound bulk super sacks, enhanced their efficiency, reduced material handling costs. Here are some of the key takeaways from what I've discussed earlier. I've discussed some of the key approaches to chemical stability, and these strategies include use of antioxidants and preservatives to prevent oxidation, slowing down degradation reactions by using pH control, encapsulation to protect sensitive ingredients to enhance shelf life, light and oxygen barriers to prevent chemical deterioration. Physical stability strategies include moisture control to prevent crystallization, caking, and phase separation, emulsion stabilization to maintain uniformity in liquid products, particle size optimization to prevent sedimentation and improve flowability. Again, temperature management, reduce physical degradation. The flowability strategies, again, include anti-caking agents, moisture control, particle size optimization, where ensuring uniform particle size will enhance flow and flowability. Equipment and process optimization, again, advanced mechanical instruments, including feeders and agitators, ensure smooth movement, advanced hopper design to reduce blockages, and automated monitor to detect inconsistencies in real time. And finally, balancing stability and flowability. These strategies include ingredient and formulation adjustments to control particle size to prevent segregation, moisture management to prevent clumping while preserving product integrity, and emulsifiers and stabilizers to enhance stability without compromising flowability. In terms of physical, we can use processing and equipment optimization, again, to prevent powder bridging, improve flow without destabilizing ingredients, detect inconsistencies in real time to adjust processing parameters. Environmentally, Packaging and storage innovations include atmospheric packaging controls to reduce oxygen exposure to enhance stability, ensuring smooth dispensing and storage. Temperature regulation, of course, and bulk handling systems can optimize storage solution to prevent separation of ingredients. I hope that I've helped you understand why stability and flowability are critical in food and beverage manufacturing. You can see some of the key challenges faced by manufacturers and how innovation addresses them. Now I will hand this webinar over to my partner, Viola Chen, to explain how you can perform powder characteristic analyses as well as formulation stability analysis with some interesting case studies in part 2 of this webinar.
Thank you, Dr. Barnum, and hello, everyone. I'm Viola Shen, application scientist of Bettersize Instruments. Now let's explore the analytical approaches used to examine powder characteristics and formulation stability in food and beverages. My sharing will cover the three main topics: food powder characteristics, formulation stability analysis, and a case study demonstrating how these techniques improve production efficiency and customer satisfaction. Well, speaking of improving efficiency, here's the challenge in food manufacturing. When you optimize one powder property, like tap density, it may negatively affect another, such as dispersibility. So this piecemeal approach leads to constant trial and error, wasting time and money. That's where the PowderPro comes in. As an all-in-one solution, PowderPro A1 is a powder characteristic tester that streamlines powder analysis. It can measure 14 key parameters, ranging from density to angle of repose, compressibility, and more. This comprehensive approach helps reduce manual error and save valuable time in R&D and QC. So whether you are working with nutritional powders, protein supplements, or functional food ingredients, PowderPro A1 helps ensure the optimal processability and the smoother production workflow from raw materials to your final products. Let me walk you through the details of this instrument. The PowderPro A1 provides a highly compact and efficient solution with several notable advantages. It can provide standardized results that comply with USP, ISO, ASTM, and other industry standards. For manufacturers working with food powders, features like GMP compliant workflows and FDA 21 CFR Part 11 compliance help ensure traceability, data integrity, and regulatory readiness. To further enhance its analytical capabilities, the PowderPro A1 also comes with a built-in sieving function, making it easy to analyze particle size distribution. And this feature is especially valuable in food powder applications where particle size directly affects flowability, solubility, and mixing behavior. It's also equipped with a high-resolution CCD camera that captures clear images of the powder pile, allowing accurate and repeatable measurements of key flowability parameters like the angle of repose or angle of spatula. All these specialties make PowderPro A1 a reliable tool in regulated production environments. Therefore, in the next case, we will demonstrate how these advanced functions work together in practice. In cocoa powder production, defatting is used to adjust fat content. This helps control powder properties and extend shelf life and boost product value. So, for instance, low-fat cocoa works well for baking, while medium to high-fat types gives hot chocolate smoother texture. And here, the figure is the manufacturing workflow of cocoa solids. There are two main defatting methods, the hydraulic pressing and screw pressing. They lead to different fat levels and powder flowability, which directly affect the production efficiency.
In this case, we need to quantify the difference between the two techniques so as to connect fat content of cocoa solids to their process performance and avoid production issues like clogging or downtime. And here are the results from PowderPro A1, which is based on the car index method with angle of repose, angle of spatula, densities, compressibilities, and uniformities in consideration. The flowability index showed that the hydraulically pressed cocoa powder exhibits better flowability than the screw-pressed samples because its flowability index is bigger. And also from this table, we can even find out why their flowability differs. The reason lies in particle size uniformity, represented by the D60 and D10 ratio, which quantifies the width of the particle size distribution. As high ratios with uniformity value above 3 generally indicates broad particle size ranges and relatively poor uniformity. So in this case, the screw-pressed cocoa sample shows a higher uniformity ratio correlating with agglomeration issues during its real production. And this issue is being addressed by optimizing the grinding process to achieve more uniform particle sizes. Therefore, we know that by analyzing these parameters, manufacturers can identify the root causes of flow issues such as poor density control, oversized particles, or even non-uniform size distribution. This systematic approach enables data-driven adjustments to optimize production and also ensure consistent product quality. While the PowderPro A1 excels at analyzing powder flowability, liquid and semi-solid food products like beverage, beer, and yogurt pose distinct stability challenges. So how do we define the stability in these systems? And more importantly, how can we quantify issues like sedimentation or aggregation that may occur during production? This time, the answer lies in the BeScan Lab Stability Analyzer. It is a versatile and reliable stability analyzer built on static multiple light scattering, the SMLS technology, which is an optical method to characterize sample in terms of real-time stability. As the figure showing the right side, this technique emits light into the sample, where it is scattered multiple times by particles or droplets before being detected by two detectors. One is the 0-degree forward detectors, and the other one is the 135-degree backward detector. As shown in the figure, the detectors and the LED lights are located in a platform. The platform moves up along the heights of the bottle and collects signals every 20 microns. And also in BeScan Lab, each complete scan collects light intensity data throughout the sample, and this data is then converted into a numerical value, the instability index, and it can be get from this specific formula. Each scan yields one instability index, which reflects the degree of instability at the moment. While by performing multiple scans over time, we obtain a series of instability index values. And these values are then plotted as points and forming a trend line on the graph with time on the x-axis and the instability index on the y-axis. Then we can get an instability plot. In this instability plot, we compare these colorful lines across 4 samples, giving both a quantitative measure of stability and a clear visual comparison. So here we can see that the pink line is the flattest, suggesting it's the most stable sample among the group. And now let's take a look at how this method is applied in 2 real-world examples. The first case on the left compares stability of yogurts with different prebiotics. The results show that yogurt containing prebiotic A has a stability index value comparable to that of the blank sample, indicating that it does not negatively affect the yogurt's original stability. This helps manufacturers select a suitable prebiotic that maintain the product's natural stability while still delivering functional benefits. And the second case on the right side measures milk tea stability of fructose. Since stability affects textures, visual appeal, and ingredient separation, it is essential to determine how sweetness impacts the formulation. The graph shows that as more fructose is added, the instability index increases, indicating lower stability. And this finding is valuable for optimizing sweetness levels while maintaining a stable, high-quality product. In all these cases, we tested multiple food sample stability. To level up efficiency, we also provide simultaneous measurements of up to 10 samples are possible, controlled by only one single soft interface. And our one-to-many system saves time and adds measurement flexibility as each BeScan lab can be controlled independently. Now that we've learned about these two powerful instruments, let's look at how combining them helps solve real-world challenges in protein powder production, from processing issues to improving drinking experience. This customer is a nutrition manufacturer producing the protein powders with varying content to meet different market needs. They provide from high protein formulas for fitness enthusiasts to low protein products for elderly and children's nutrition. While this variety broadens their product line, it also brings processing and some QC challenges. For example, in their production line, they met frequent powder clogging at feeding outlets and sometimes low packing efficiency issues. And on the product side, the powders often fail to dissolve properly, leading to poor mouthfeel and visible instability, which surely affects its shelf life. By understanding these challenges, we can help them to quantify the impact of protein contents on both flowability and stability, so as to optimize their production and product design. For the first production bottlenecks, we can use the PowderPro A1 and the car index method. Also, we found a clear trend as protein content increases from 20% to 50% to 80%. The flowability index drops sharply, indicates its significant decline in the flowability. The reason is that higher protein content leads to more particle aggregation, which increases friction and causes clogging during the production, especially in the 80% sample. The further analysis of the data reveals critical differences in density and compressibility across the samples. Compressibility increases from 26% to about 35%, suggesting stronger particle cohesion and reduced structural stability with increasing protein contents. At the same time, both the tap and bulk densities decreased, meaning more volume is needed to pack the same weight of powder. In their real production, this actually caused issues like overfilling or underfilling. The low-density protein powders occupy more space, often requiring larger packaging or more frequent refills to hit the target weight. This not only increases cost, but also poses challenges for automated filling system. Well, by addressing these density-related issues, manufacturers can optimize packaging and improve dosing accuracy also reduce the material waste. To evaluate and optimize formulation stability, we use the BeScan Lab after preparing the protein powders into liquid formulations. This figure presents the global instability of the 3 protein samples. Among them, the 80% protein sample shows the highest instability index, while the 20% one shows the lowest instability index and the smoothest slope. This indicates that the formulation with the highest protein concentration exhibits the most pronounced overall instability. So, what does this instability refer to specifically? Well, to answer this, we can refer to the spectral plots generated by the software, which offer further insights into the types of instabilities occurring, such as phase separation, aggregation, or particle migration. When protein powder comes into contact with water, it typically goes through these 5 key stages. And how well the powder moves through these stages determine its overall stability in the formulation. In this example, its overall stability is related to its solubility, as indicated from the transmission data plots in the upper right corner. The transmission intensity reflects how much light passes through the sample, and a clear, well-dissolved solution allows more light through, resulting in higher transmission values. So, in this figure, the 20% protein sample shows the highest transmission, indicating better solubility than the others. To better understand their difference in solubility, we can look at the 3 transmission spectrums in detail. In this spectra, the x-axis shows the height of the sample cell, and the y-axis shows the transmission intensity. The blue line is the signal at the beginning of the test, and the red line is the signal at the end. From the first spectrum of the 20% protein, we can clearly see that over time, the transmission intensity at the bottom decreases, while the intensity at the top increases. More light can go through the top layer. This indicates that most particles dissolve well before forming a sedimentation layer at the bottom. Well, compared to the 20% sample, the 50% one shows smaller changes in transmission intensity at the bottom, suggesting the sedimentation and aggregation still occur, but to a lesser extent. In the middle and upper section, there are visible bumps in the lines, which indicates it has uneven distribution and less uniform due to its incomplete dispersion and suspension. While the last figure shows the results of the 80% protein sample, and this one behaves very differently. There's no increase at the top and also no decrease at the bottom. This tells us that the powder fails to wet properly at the very beginning at such a high concentration. Instead, the undissolved material floats and clumps at the top, forming a dense layer that blocks light, resulting in consistently low transmission in the upper region. By identifying this weakness early using tools like BeScan Lab, formulators can adjust ingredients or processing steps to improve product stability by adding wetting or dispersing agents so as to ensure a better consumer experience. This case clearly shows how protein content affects not only the powder flowability but also the final formulation stability. In this case, differences in flowability stem from densities and compressibility, while varieties in stability are mainly due to dissolution and wettability behavior. By combining PowderPro A1 and BeScan Lab, we can quantify key physical and stability related parameters of food products. And more importantly, we need them to identify the root causes of issues that manufacturers often face, guiding formulation improvements. our instrument can absolutely do more than just testing. They serve as powerful tools for problem diagnosis and formulation optimization. And this is exactly what Bettersize strive for, to provide comprehensive solutions for understanding, monitoring, and improving material performance. And that's all for my today's sharing. Thank you, everyone.
Thank you, Beverly and Viola, for those informative presentations. If you have a question for either of our presenters, now would be the time to submit it through the Q&A panel on your screen. While we wait for everyone to submit their questions, let's do a few quick polling questions for you guys. Our first question that you should see on your screen is, which area of your production process would benefit most from improved particle or flowability analysis? Raw material QC, R&D and formulation, powder or liquid packaging or handling packaging, packaging and final product consistency, or other? Go ahead and give us your answer. We'll look at these. Right, it looks like most everybody said R&D formulation as well as other. So there's a few options there. Right, let's go to our next polling question. Right, polling question number 2. How are you currently measuring powder flowability or stability? Are you using in-house equipment, outsourcing to third-party labs, manual visual estimation methods, still exploring your options, or are you not measuring currently at all? All right, it looks, oh, well, we got like an even tie for for 4 of the answers. So 25, 25%, 25%. So that's pretty cool. All right, last question. Or actually, I think that's it for now. And we will go ahead and move on to our Q&A. All right, our first question is for Viola. Viola, are you ready for us?
Yes.
Perfect. Viola, this customer they say we use angle of repose. Do we need to use the car index?
Well, yes, angle of repose is definitely a useful indicator, but it only reflects one aspect of powder flowability, mainly how the powder piles under gravity. While in reality, powder flow is influenced by many other factors like compressibility, cohesion, and particle uniformity. So the car index method brings these parameters together to give a more complete and accurate picture of how your powder behaves during the handling, filling, or transport. So this is especially important for food product powders, which are often affected by things like moisture content, fat, or particle shape. So while angle of repose is definitely a good starting point, but relying on it alone can lead to incomplete or even misleading conclusions. So, well, for a comprehensive analysis of powder flowability, I would strongly recommend a powder characteristic tester, maybe like PowderPro A1. Yes.
Perfect. Thank you, Viola. Another question for you before we jump over to Beverly.
Okay.
Viola, what is the sample amount required for the Powder Pro AI? A1, I'm sorry.
The PowderPro A1 typically needs about 150 to 200 milliliters of powder for a whole flowability measurements. That's because the powder flowability testing relies on physical movement, like how the powder piles up and how it's flow down a chute or get compact. So to simulate real flow behavior accurately, we need enough material to form a proper powder pile or fill the test chamber. If your sample is too little, too small, it just can't reflect actual handling conditions, and the result may not be that reliable. And also, since the instrument measures multiple parameters in one sequence, like first we do bulk and tap density, and then the compressibility and angle of repose, and then all using the same sample. So having enough material ensures the whole test runs smoothly without interruption. So that's why a slightly larger sample amount is needed.
Of course. All right. Before we jump over to Beverly for a couple questions I see in the queue, we're going to ask our final poll question, audience. Are you currently evaluating new tools for particle size, powder characteristics, or stability analysis in your processes? Yes, you're actively looking, planning to buy this year, just exploring options, or not at the moment. If you take a moment to let us know on this final poll question, we'll take a look at the results before we jump back into our Q&A with Beverly. All right, it looks like the majority, about half, are just exploring options, which is perfect given this webinar. So we will continue to talk about it as you think about your options and see what your options are, such as what we're talking about right here. So Beverly, on to you. Our first question for you is, what are common formulation mistakes that lead to poor flowability or stability?
All right. Common formulation mistakes that can negatively impact flowability and stability include inconsistent particle size distribution, where a wide particle size distribution can lead to segregation, which causes uneven flow. And if you have excessive fine particles, if you have too much fines, then this will increase the cohesion, which leads to poor flow, and then this would lead to equipment blockages. As always, high moisture content in the environment. Um, Also, having the incorrect bulk density. Low bulk density powders don't flow well, while high density powders can cause bridging. And Viola had mentioned the low density bulk powders being an issue for the protein powders, and a lack of flow aids. So, if you have these issues, you can add anti-caking agents to help overcome the poor powder movement. In terms of stabilities for non-powders, so not using stabilizers, so you can add emulsifiers or antioxidants, excuse me, to lead to keep to overcome poor powder or liquid movement. Um, s- Excuse me, and stopping phase separation or oxidation, and then poor ingredient compatibility is sort of the mystery magic that not realizing that some ingredients react over time, or the combination of ingredients react over time, and this will cause degradation. This is where a stability test would be quite useful. Incorrect processing conditions, again, talking about temperature, humidity, but also shear forces. So if your stirring rate is too high, ultrasound, you can destabilize an emulsion that you just added these emulsifiers to assist with, or break down powders. And then failure to control the pH, which will lead to degradation or loss of functionality. And then, of course, packaging nowadays, where exposure to air or light or moisture, again, the evil, can accelerate instability.
Perfect. That makes sense. All right. Well, another question here for you then, Beverly. Someone says, what powder parameters can I measure to help prevent production issues?
Well, Viola has discussed many of these, but some of the flowability related parameters are the angle of repose, using the PowderPro to get to the car indices, using the Hausner ratio, which will assess powder compressibility and the like, and this will help you assess if the probability of having flow issues, flowing through an orifice, like a hall funnel, etc., can measure how quickly the powder passes through an opening. And this can help you identify clogging risk. Again, particle characteristics, particle size distribution affects the flowability, the density, and segregation tendencies, shape and surface texture, where irregular shapes can lead to poor flow and increased cohesion. We haven't discussed that much too in depth here, but there are instruments that can address this, bulk and tap density, as Viola had mentioned earlier, and of course, my favorite, moisture content. Again, excess moisture lead into clumping, and actually having very low humidity can lead to dusting, which kind of leads us towards electrostatic charges, which can impact negatively, where we can get powder adhesion to the equipment surface, so it's static to the surface. This is more related to floodability, and then finally temperature, of course. So these are things that you can control and measure. So
Perfect. Thank you, Beverly. Viola, another one for you.
Okay.
Customer says, we are still under R&D, so our sample of formulation is in limited supply. Can BeScan Lab still analyze it?
Oh, yes, absolutely. BeScan Lab is designed with low volume sample cell needs. So it only requires about 2 to 4 milliliters per cell. So, from my experience talking with the food customers in their early stage formulation work, being able to track their stability trends with minimum material is very important. So BeScan Lab uses the non-destructive static multiple light scattering techniques, meaning your sample remains intact throughout the test and can be used for follow-up analysis or comparison for the later process. So even if you only have a small batch from a lab mixer or the pilot line, you can still evaluate how stable your protein blend, emulsion, or the suspension is without waiting for scale up.
Perfect. All right, well, we're running out of time, but I think we have time for one more question for you. So, our last question is from a customer says, we're running multiple stability tests on different formulations at different temperatures. Can BeScan Lab handle this type of setup also?
Yes, yes. As I mentioned before, our BeScan Lab provides the one-to-many functions that can help you with this, and you can connect up to 10 BeScan units to a single PC, and using just one software platform to control all of them. And each unit can run its own SOP. So you can measure all the samples under different temperature conditions and testing different samples simultaneously. So this means you don't need to invest in multiple computers or a license, and you save a lot of time by running all your tests in parallel. So it's super ideal for formulation screening, stability comparison, and the high throughput R&D workflows.
Perfect. All right, yeah, that sounds great. All right, well, audience, that is about all the time we have today for our Q&A. Before we go, I'd like to thank our fantastic presenters, as well as Bettersize, the sponsor for today's webinar. In 24 hours or less, this webinar will be available on demand if you'd like to watch it again or share it with friends and colleagues. Our next webinar, sponsored by Bettersize, will be held on July 16th, and we hope to see you there again. Have a great day, everyone.